May 27th, 1944. 16,000 feet above the Marshall Islands, Lieutenant Hiroshi Nakamura banks his Mitsubishi A6M Zero fighter through broken cloud, watching tracers arc up from the American destroyer below. He's survived 41 combat missions by understanding one simple truth. Anti-aircraft shells must hit you to kill you. Stay between the bursts. Change altitude constantly. Never fly predictable patterns. The mathematics of survival are straightforward. A 5-inch shell creates a lethal radius of perhaps 20 feet if it scores a direct hit. The odds of that happening? Astronomical. Naval gunners fire thousands of rounds for every aircraft they destroy. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Nakamura learned this over Guadalcanal, over Rabaul, in the skies above the Solomons. He'd watched green pilots panic at the sight of black bursts, diving away from barrages that were never going to touch them. The veterans knew better. You respected the flak, gave it room, but you didn't fear it. Not really. The Americans had guns, yes, hundreds of guns, but their ammunition operated on the same principle as everyone else's. Clockwork fuses timed to explode at predetermined altitudes. Miss the altitude calculation by 3 seconds, and the shell bursts in empty air. What Nakamura doesn't know, what no Japanese pilot knows as they approach American task forces in the spring of 1944, is that the rules of anti-aircraft warfare have been rewritten. The shells rising toward him no longer need to hit anything. They carry their own eyes, their own decision-making apparatus, their own trigger. They are hunting him with radio waves, measuring the shrinking distance with electromagnetic precision, waiting for the perfect moment to detonate. Not on impact, near impact. The difference is about to become the difference between calculated risk and mechanized slaughter. The destroyer below is the USS Prishet. Her 5-inch 38 caliber guns have just been loaded with ammunition marked only with the cryptic designation VT, variable time. The gunners don't fully understand what they're firing. They've been told the fuses are experimental, classified, to be used only over water where duds can't be recovered by the enemy. They've been shown the results in training exercises. Drone aircraft obliterated with 4, sometimes 3 shells, a kill rate that seems impossible. Chief Petty Officer James Morrison watches his gun crew load the VT rounds into Mount 51. He's been firing 5-inch guns since 1942, spent hundreds of hours calculating time fuses, estimating range, altitude, target speed, trying to place explosive shells in the exact cubic meter of sky where an enemy aircraft might be 15 seconds from now. It's an art built on mathematics and prayer. The odds are terrible. You learn not to expect hits. You fire to frighten, to disrupt attack runs, to force pilots to jink and weave and drop their bombs inaccurate. But these new shells. Morrison has seen what they do. In Chesapeake Bay, during the abbreviated training his crew received before deployment, they'd engaged radio-controlled targets at 12,000 yards. The targets didn't stand a chance. Shells that should have been near misses, passing 50, 70, 100 feet from the drone, detonated anyway. Perfect bursts, creating overlapping fields of shrapnel. The mathematics of anti-aircraft fire had fundamentally changed, and the Japanese were about to learn this in the most unforgiving classroom imaginable: combat. Nakamura begins his dive, committing to the attack run. He's targeting the destroyer, planning to strafe the bridge and forward guns before climbing away. Standard tactics. He's done this before. The ship's guns open fire at 9,000 yards. Much earlier than optimal, he thinks, wasting ammunition. The Americans are nervous today. The first proximity fuse that kills a Japanese aircraft in this engagement costs $18 to manufacture. It was assembled 6 weeks ago in Cincinnati, Ohio, at the Crosley Corporation factory by women who thought they were building radio parts. The fuse contains 130 miniaturized components, including vacuum tubes engineered to survive 20,000 times the force of gravity. Normal vacuum tubes, the kind in a radio or radar set, are fragile glass envelopes that shatter if you drop them. These tubes have been redesigned at the molecular level, their glass composition altered, their internal elements spot-welded and potted in shock-absorbing compounds, tested to destruction until only the strongest survive. The transmitter inside the fuse broadcasts a continuous radio wave at 190 MHz. When that wave reflects off Nakamura's Zero, it returns with a slight frequency shift, the Doppler effect, the same principle that makes a train whistle's pitch change as it passes. The fuse's receiver detects this shift, measures it, calculates the rate of closure. When the mathematics indicate the shell is 70 feet from the target, a thyrotron tube fires, sending current to the detonator. The entire sequence takes milliseconds. Nakamura sees the burst, not ahead of him, not behind him where he's already flown, but beside him, impossibly precise, as if the shell knew where he was and chose to explode at exactly that moment. The blast wave hits his Zero like a physical blow. Shrapnel, thousands of steel fragments traveling at supersonic speed, tears through the aircraft's light aluminum construction. His hydraulics fail first, then his controls. The Zero, which moments ago was a responsive extension of his will, becomes a falling object governed only by gravity and aerodynamics. He doesn't understand what happened. The shell didn't hit him. He's certain of that. He would have seen impact, felt it, known it. This was something else. Something that violated his understanding of how artillery functioned. In the 17 seconds before his aircraft impacts the Pacific Ocean, Hiroshi Nakamura dies confused, not just about his immediate death, but about the rules that were supposed to govern aerial combat, the mathematics that had kept him alive through 41 missions, the predictable patterns of American anti-aircraft fire that had suddenly become unpredictable in a way he couldn't comprehend. On the bridge of the Prichot, the fire control officer marks one enemy aircraft destroyed. He's surprised by how few rounds it took. 8 shells fired, 1 kill. The ratio should be closer to 1,000 to 1. His gunnery officer reports the VT fuses, performed as advertised. The Admiral will want confirmation, photographic evidence if possible, because these results seem too good to be true. They are true, and they are about to become the new normal. To understand why the proximity fuse represented such a profound shift in naval warfare, you have to understand the problem it solved. Anti-aircraft gunnery had always been an exercise in predicting the future. A 5-inch gun fires a shell that weighs 54 pounds and travels at 2,500 feet per second. Sounds fast. It's not fast enough. A dive bomber at 10,000 feet, moving at 250 miles per hour, can change position by over 100 feet in the time it takes your shell to reach that altitude. So the gunner must calculate target range, target altitude, target speed, target heading, wind speed, wind direction, the ballistic arc of his own shell, the precise moment the time fuse should detonate. All while the deck is pitching, the target is maneuvering, smoke and chaos obscure vision, and the knowledge that if you get it wrong, that bomber might put a 500-pound bomb through your ship's deck. The mechanical time fuse, standard equipment, since the late 19th century, was a clockwork device, literally, a spring-wound mechanism that burned or ticked down to detonation. Gun crews set them by hand, twisting the fuse to a specific number based on range calculations. The margin for error was enormous. Set it too short and the shell bursts before reaching the target. Too long and it explodes above or beyond the aircraft. The three-dimensional geometry of aerial combat meant that even small errors in calculation translated to hundreds of feet of missed distance. At Pearl Harbor on December 7, 1941, American anti-aircraft batteries fired over 1,400 5-inch shells at Japanese aircraft. They achieved approximately 3 confirmed kills. The ratio, 1 aircraft destroyed per roughly 500 shells fired, represented the absolute ceiling of time-fused ammunition effectiveness under combat conditions. And that's being generous with the statistics. Many shells malfunctioned, many fell back to Earth unexploded. Some detonated over Honolulu, killing civilians, adding friendly fire to the day's horror. The Japanese, attacking Pearl Harbor, faced negligible anti-aircraft fire because American forces were unprepared, guns unmanned, ammunition locked away. But when they returned to strike other targets, when they encountered prepared defenses. They learned the same lesson American planners already knew. Anti-aircraft fire with time fuses was primarily a psychological weapon. It frightened pilots, disrupted their aim, forced them to attack through walls of black bursts and near misses, but it rarely killed them, not in numbers sufficient to stop a determined attack. The mathematical problem was simple to state, impossible to solve with existing technology. You needed the shell to detonate when it was close to the target, not when a mechanical clock decided it should detonate. Close to the target meant the shell needed to know where the target was. No implied sensing, detection, decision-making. How do you give a shell the ability to sense its surroundings when that shell experiences forces that would pulverize any delicate mechanism? Dr. Merle Tuve, physicist, radio expert, former Carnegie Institution researcher, heard about the problem in August 1940. He was not a weapons designer. His expertise was magnetism and ionosphere research, esoteric physics with no apparent military application. But he understood radio, understood wave propagation, understood that radio waves reflect off metal objects. What if, he proposed, you could put a tiny radio transmitter and receiver inside a shell? What if that radio could detect the reflected signal bouncing back from an aircraft? What if you could measure the strength of that reflected signal and use it to trigger detonation at optimal range? The concept was elegant. The engineering was borderline impossible. A 5-inch naval gun generates approximately 20,000 times the force of gravity when fired. For perspective, a fighter pilot experiencing 9 Gs during a hard turn is approaching the limits of human consciousness. 20,000 Gs is not a force, it's a cataclysm. Every component in the shell experiences acceleration that should turn sophisticated electronics into powder and fragments. Vacuum tubes, the only electronic amplifiers available in 1940, were glass envelopes containing delicate wire filaments and metal plates suspended in vacuum. Drop one on the floor, and it shatters. Fire it from a naval gun, and you should get glass dust and broken dreams. Tuve's team at Section T, a newly formed division hidden within the National Defense Research Committee, had to reinvent vacuum tube construction from basic principles. Sylvania Corporation in Ipswich, Massachusetts, became the primary manufacturer. Women, mostly women, worked in a facility so secret that local police weren't allowed inside, that required workers to be searched, entering and leaving, that forbade personal items, that manufactured components whose purpose was never explained. The tubes they built were miniature miracles. Less than 1 inch tall, glass walls twice as thick as normal tubes, using special high-strength glass formulations, internal elements spot-welded instead of soldered, everything potted in shock-absorbing material. By spring 1941, after thousands of test firings and thousands of failures, Sylvania produced tubes that could survive 20,000 Gs and still function. Each tube had to be tested individually. You couldn't quality control test a batch by firing a random sample, because each tube would be destroyed in the test. So they developed non-destructive testing methods. X-raying for internal defects, electrical testing for performance, careful visual inspection under magnification. The reject rate was high. Production was slow. The United States needed millions of these tubes. And Sylvania delivered. The power supply presented its own engineering nightmare. Batteries, as commonly understood, don't survive being fired from guns. The shock disrupts the chemical reactions, cracks the casing, causes internal shorts. The solution came from an unexpected direction: the centrifugal battery. A sealed glass ampule contained liquid electrolyte and metal plates. When the shell spun, and 5-inch naval shells spin at 30,000 revolutions per minute for stabilization, centrifugal force drove the electrolyte outward into contact with the plates, generating electrical current. No spin, no power, perfect safety. The battery was inert during storage and handling, activated only by the physics of launch. The radio circuitry itself had to fit in a nose cavity roughly 2 inches in diameter. The transmitter, receiver, amplifier, detector, and detonator control all had to coexist in that tiny space, All had to survive the launch. All had to function while spinning at 30,000 RPM. The design that emerged used 4 vacuum tubes, a handful of capacitors and resistors, a tiny antenna, and a detonator. The antenna was built into the nose cone, a simple ring that radiated and received radio frequency energy forward from the shell. The physics of operation were based on the Doppler effect, but implemented in a way that was robust and simple. The transmitter broadcast continuously at a fixed frequency. The receiver listened for reflections. When a reflection came back, it was shifted in frequency because the shell was moving toward the target. The amount of frequency shift depended on closing speed. Mix the transmitted and received frequencies together and you got a beat frequency, an audio tone difference frequency that could be detected and amplified. When that beat frequency indicated the shell was approaching the target at the right speed and distance, typically 70 to 80 feet, fire the detonator. The entire system had to make this decision in milliseconds, had to function reliably despite being spun, heated, vibrated, and subjected to forces that would destroy any commercial electronic device. And it had to be manufactured in quantities of millions, at costs that made sense for expendable ammunition. The proximity fuse program would eventually involve over 100 companies, 110 factories, and cost over $1 billion. More workers than the Manhattan Project. More industrial coordination than building Liberty ships. May 6, 1941. Dahlgren Naval Proving Ground, Virginia. 6 prototype fuses were fitted to bombs, not shells, and dropped from aircraft over the Potomac River. Radio-controlled boats served as targets. The bombs, falling at a relatively gentle few hundred Gs compared to artillery launch, kept their electronics intact. The radio fuses detected the boats, triggered detonation at programmed altitudes. It worked, proof of concept achieved. But bombs and artillery shells live in different worlds of violence. The next, test, artillery launch, seemed likely to destroy every carefully built component. August 12, 1942, Chesapeake Bay. The cruiser USS Cleveland fires production version VT-fused shells at radio-controlled drone aircraft. The drones are expendable, built specifically to be shot at, flying predictable patterns. 3 targets, 3 kills, 10 shells fired total. The fuses survived launch. They detected targets. They detonated at proper range. The impossible had become merely difficult. The U.S. Navy, characteristically cautious about new technology, began limited distribution. Proximity fuses were authorized for use only over water, where enemy forces couldn't recover unexploded rounds and reverse engineer the technology. Ships received small allocations, carefully controlled. Gunners were trained on their use, but told nothing about the mechanism. The designation, VT for variable time, was deliberately misleading. Let the enemy think these were just better mechanical, time fuses, not radio-guided precision devices. Production ramped slowly through 1942. The fuses were expensive, $30 each initially, and manufacturing was still being refined. Western Electric, RCA, Eastman Kodak, Crosley Corporation, dozens of contractors built components. Johns Hopkins Applied Physics Laboratory coordinated technical development. Women assembled fuses in factories across the industrial Midwest and Northeast. Each fuse contained roughly 130 parts. Each part had to meet tolerances measured in thousandths of an inch. Each finished fuse had to be tested without destroying it. By late 1942, production reached 10,000 fuses per month. By mid-1943, 70,000 per day. The learning curve was brutal, the quality control intense, but American industrial capacity, once committed, was overwhelming. What had been a laboratory curiosity became standard ammunition, loaded into magazines alongside. Traditional shells, marked with special colors and codes to distinguish them from conventional ordnance. The operational security around VT fuses was obsessive. Ship captains were ordered to use them sparingly, to avoid patterns that might reveal their existence to enemy intelligence. Dud rounds that failed to explode were to be recovered if possible, scuttled if not. Pilots were told nothing about how the new shells worked. Even friendly aircraft had to be careful. because a proximity fuse couldn't distinguish between enemy and friendly metal. The radio waves reflected the same, regardless of whose insignia was painted on the aircraft. But by January 1943, enough VT-fused ammunition had reached the Pacific Fleet that its use could no longer be avoided. Japanese air attacks were intensifying, the Solomons Campaign, the grinding attrition around Guadalcanal, New Georgia, the slot where Japanese destroyers ran supplies under cover of darkness and American ships intercepted them. This was warfare, where every advantage mattered. Admiral Halsey authorized VT fuses for general anti-aircraft use in his command. The results were about to become obvious, January 5, 1943. The engagement that opens this story was not the first time VT fuses were fired in anger, but it was the first time they achieved a confirmed kill at sea. The Japanese pilot died confused because confusion was inevitable. He had no framework for understanding shells that exploded near him rather than hitting him. No way to know that American industry had miniaturized radar technology and hardened it to survive artillery launch. No reason to suspect that the rules governing anti-aircraft fire had changed at the most fundamental level. For Japanese naval aviation, still confident after their victories of 1941 and early 1942, still believing their superior training and warrior spirit gave them advantage, the proximity fuse represented a technological surprise for which there was no tactical counter. You couldn't evade shells that adjusted their detonation dynamically. You couldn't use superior maneuverability to defeat ammunition that didn't require precise aim. The only defense was not getting close enough for the shells to reach you, which meant not attacking at all. Word spread through the Japanese fleet slowly, incompletely, confused. Pilots reported shells that exploded without hitting anything, creating patterns of bursts that seemed to track aircraft movements. Intelligence officers wrote reports speculating about magnetic fuses, acoustic triggers, even radar-guided shells, which would have been closer to the truth but still missed the elegance of the actual solution. No one guessed radio proximity detection, because no one believed electronics could be built, that small, that rugged, that cheap. The Japanese had excellent engineers, sophisticated industry, advanced physics programs. They knew about radio, about radar, about vacuum tubes, and electronic amplification. What they didn't have was the industrial infrastructure to produce millions of miniaturized components to exacting tolerances, or the organizational capacity to coordinate hundreds of contractors building parts for a single integrated system, or the massive financial investment required to develop technology whose payoff was uncertain. Germany faced the same problem. German scientists had actually conceived of proximity fuses before the war, had developed over 30 different prototype designs, had conducted extensive testing, but they concluded the technology was impractical, impossible to manufacture in military conditions, too fragile to survive artillery launch. They were wrong, but their reasoning was sound given German industrial capabilities. What they failed to anticipate was that American engineers would solve the problem through brute force, testing thousands of designs, iterating relentlessly, throwing industrial capacity at every obstacle until solutions emerged. The impact of proximity fuses on Japanese naval aviation became statistically visible by mid-1943. American ships were shooting down more aircraft per shell fired. Not dramatically more at first, because time-fused ammunition still made up the majority of rounds fired, but enough that Japanese losses were climbing, while American defensive capabilities were improving. The attrition mathematics, already unfavorable for Japan due to American industrial superiority, became untenable. Training experienced pilots took months. Japan started the war with roughly 3,500 carrier-qualified aviators, the best in the world, veterans of combat in China, trained to exacting standards. By mid-1943, that elite corps was being ground down, killed in combat faster than replacements could be trained. And the replacements were facing defenses their predecessors had never encountered. Technology that invalidated the hard-won tactical knowledge that should have given veterans advantages. A proximity fuse didn't care if the pilot attacking was an ace or a trainee. It measured range with radio waves, calculated optimal detonation with electronics, executed with mechanical precision. Human skill mattered less when the ammunition was smart enough to compensate for mediocre gunnery. An average American gun crew with VT fuses could achieve kill rates that would have required expert crews with time-fused shells. The skill floor had been raised, the playing field leveled, advantage redistributed from training and experience to industrial production and technological sophistication. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. June 19th, 1944. Philippine Sea. The largest carrier battle in history is about to begin, and Lieutenant Commander Akira Tamaya stands on the flight deck of the carrier Taiho, watching 373 aircraft prepare for launch. Admiral Jisaburo Ozawa has promised this will be the decisive engagement, the battle that will crush the American carrier force and reverse 2 years of retreat. Tamaya has reviewed the pre-flight intelligence reports, and something troubles him. Reconnaissance pilots mention unusual patterns in American anti-aircraft fire, shells that explode without hitting anything, creating clouds of shrapnel at precise distances from Japanese aircraft. His pilots have trained extensively for this moment. They know American 5-inch 38 caliber guns, know the predictable patterns of time-fused shells, know that sudden altitude changes and radical evasive maneuvers at critical moments can defeat gunfire that requires precise calculation of detonation time. What they don't know, what no amount of training has prepared them for, is that American effectiveness has quadrupled overnight. That shells no longer need calculation. That near misses are now kills. The first wave launches at 0830 hours, perfect formations, Zeros escorting dive bombers and torpedo planes, veterans who survived the Solomons, New Guinea, battles where they learned American patterns and believed they could overcome American technology through superior spirit and determination. Within an hour, these veterans would be dying in confusion, unable to comprehend why shells were exploding beside them, around them, in perfect proximity without ever touching their aircraft. Lieutenant Saburo Shindo leads the fighter escort, 37 combat missions, 11 confirmed kills, an ace by any measure, one of the dwindling number of experienced pilots still alive in Japanese naval aviation. He approaches Task Force 58 at 23,000 feet, planning his dive to minimize exposure to anti-aircraft fire. The American formation appears on the horizon, 40 miles of ocean, carriers protected by rings of battleships, cruisers, destroyers. Formidable. But Shindo has penetrated such defenses before. At 12,000 yards, the American guns open fire. Shindo sees muzzle flashes, sees shells climbing toward his formation. But something is different. The shells aren't following predictable patterns. They're not exploding at preset altitudes based on calculations made seconds ago. They're tracking his aircraft, sensing his presence, detonating in perfect proximity. His wingman, Ensign Yoshio Fukui, disappears in a cloud of black smoke and metal fragments 500 meters to his right. The Zero disintegrates not from direct impact, but from a shell that detonated precisely 20 feet away. The proximity fuse that killed Fukui was manufactured 3 weeks earlier in Cincinnati. It detected his aircraft through phase relationship between transmitted and received radio waves. The heterodyne beat frequency generated by Doppler shift provided a signal that triggered a thyrotron tube when it exceeded predetermined amplitude. All of this occurred in the fraction of a second between the shell passing the aircraft and optimal detonation point. Technology representing over $1 billion of American investment and coordination of 87 different companies. The Japanese formation begins to dissolve. Pilots break formation in desperate attempts to escape shrapnel that seems to follow them regardless of evasive maneuvers. Their carefully planned attack degenerates into chaos as proximity-fused shells find them at ranges and angles that should have been safe according to everything they were taught about anti-aircraft warfare. Commander Tamaya, monitoring radio frequencies from Taiho's bridge, hears increasingly desperate calls from his pilots. Voices that were confident, minutes before now express confusion and fear. Shells exploding all around them without warning, creating an impenetrable wall of steel fragments, making it impossible to maintain attack formations or aim weapons properly. Petty Officer First Class Robert Martinez, gun captain on Mount 52 aboard the destroyer USS Stockham, had been skeptical when first briefed on proximity fuses. Hard to believe a radio device could survive being fired from a gun. But after witnessing drone targets destroyed with 4 shells during training, he became a believer in what the Navy mysteriously called variable time fuses to hide their true proximity sensing nature. Now, watching Japanese aircraft approach his sector, he notices they're flying the same attack patterns that had been effective against time-fused ammunition, clearly unaware that the rules of anti-aircraft engagement had fundamentally changed. The mathematics of the battle tell the story. 373 Japanese aircraft launched. 29 American planes shot down. The exchange ratio defies every projection Japanese naval planners made. American pilots would later call it the Great Marianas Turkey Shoot, though the Japanese pilots dying in burning aircraft had no way to understand why casualties were so catastrophically disproportionate. The proximity fuse was not the only factor. American radar-directed fighter interceptions played crucial roles. Superior pilot training mattered. But for Japanese pilots who survived to report back, the most incomprehensible aspect was how American anti-aircraft fire had become so unnaturally accurate, as if shells themselves could see targets, as if the laws of physics had been rewritten. Lieutenant Commander Tamiya's after-action report to Admiral Ozawa reflects the confusion and dismay permeating Imperial Navy aviation units, anti-aircraft fire that seemed to violate physics, shells exploding at perfect distances to maximize damage without any apparent aiming mechanism, as if Americans had developed supernatural sensing ability. The report reaches Tokyo, where naval technical experts struggle to explain what happened. They propose theories: magnetic sensing, acoustic triggers, never imagining Americans had miniaturized radio technology to the point where it could survive being fired from a gun. German scientists, with all their technical prowess, had attempted proximity fuses and failed, developed over 30 different designs, concluded it was impossible. Japanese engineers understood theoretical principles, but couldn't conceive of the industrial mobilization required to transform theory into millions of functional devices. The gap wasn't just technological, it was organizational, industrial, financial. America had built an entire infrastructure around making impossible electronics possible, then producing them at scale that defied imagination. The human cost for Japan was strategic. The pool of experienced aircrew was finite. Proximity. Fuses turned attrition into crisis. Trained pilots, the kind who could deliver coordinated attacks, were lost at rates replacements couldn't match. By late 1944, desperation led to kamikaze tactics. Pilots trained only to point aircraft at ships, not maneuver away. Kamikaze attacks removed the escape phase that proximity fuses exploited most effectively. But even kamikaze pilots discovered technology could defeat determination. USS Laffey, a destroyer on radar picket duty off Okinawa, April 16, 1945, faced multiple kamikaze attacks. Her 5-inch guns loaded with VT-fused ammunition created overlapping patterns of shell bursts that no aircraft could penetrate. The destroyer survived, shot down dozens of attackers, though 6 kamikaze aircraft did break through and strike home. The proximity fuse didn't make ships invulnerable. It bought time and lives in desperate battles. From October 1944 to August 1945, hundreds of Japanese aircraft were destroyed by VT rounds, many that under old systems would have survived to strike targets. Kill rates per round rose dramatically. Where time fuses required over 1,000 rounds per aircraft destroyed, proximity fuses averaged 310 rounds per kill against diving attackers. A threefold improvement that translated directly into ships saved, sailors who went home instead of dying in burning vessels. The statistics reveal the transformation. Engagements where proximity fuses were used saw aircraft kills per round increase by factors of 3 to 7 depending on conditions. At Okinawa, Japanese lost over 1,900 aircraft in kamikaze attacks, managing to sink only 26 ships, none larger than destroyers. An exchange rate, even Japanese commanders privately admitted, was unsustainable. The psychological impact went beyond mathematics. Japanese pilots who had been told spiritual determination would overcome American technology discovered. That technology they couldn't understand or counter was killing them before they could even see targets clearly. Surviving kamikaze pilots who returned due to mechanical problems reported helplessness against anti-aircraft fire that seemed to possess supernatural accuracy. Shells that found them regardless of prayers or determination. Technology that made their sacrifice meaningless rather than glorious. Captain Toshio Miyake, commanding the destroyer Yukikaze, one of few major Japanese warships to survive the war, wrote in his post-war memoir about watching American anti-aircraft fire from a distance during night engagements, describing it as sheets of fire that lit up the sky, explosions that seemed to know where aircraft were, a wall of death no amount of courage could penetrate. He had no way of knowing he was describing proximity fuses in action. Technology. Japanese scientists would study extensively after the war, marveling at American industrial achievement of mass-producing such sophisticated devices. While Japan struggled to manufacture basic radar sets, the proximity fuse represented more than technological superiority. It embodied the vast industrial and scientific mobilization characterizing American war effort, the ability to identify military need, develop revolutionary technology to meet it, then mass-produce that technology on scale no other nation could match. While German scientists had actually conceived proximity fuses before the war and Japanese engineers understood theoretical principles, neither nation possessed the combination of scientific expertise, industrial capacity, and organizational ability needed to transform theory into millions of functional devices, surviving the violence of being fired from guns. By war's end, over 22 million proximity fuses had been manufactured. What cost $732 per fuse in 1942 fell to $18 each by 1945 as factories and supply chains reached astonishing throughput. Over 100 primary contractors and thousands of suppliers synchronized manufacturing to deliver tens of thousands of fuses daily. The workers who built them, mostly women, assembled components they didn't fully understand. Ruth Horn worked at the Sylvania plant in Ipswich, Massachusetts, soldering what she thought were light bulbs, never knowing she was assembling fuses that would help win the war. She would die decades later from mesothelioma caused by beryllium exposure from her wartime work, one of thousands whose sacrifice was measured not in combat but in silent industrial poisoning, bodies ground down by the same war effort that ground down enemy aircraft in Pacific skies. The legacy of the proximity fuse extended far beyond World War II. It pioneered rugged, miniaturized electronics, hardened components surviving savage acceleration, manufacturing practices that prefigured missile guidance and smart munitions. The idea that munitions could carry their own sensors, decide when to detonate, act autonomously, traces lineage to these wartime laboratories. Lieutenant Hiroshi Nakamura, who died in the opening moments of this story, believed shells must hit aircraft to kill them. That belief, reasonable based on every previous war, every previous engagement, cost him his life. The mathematics he trusted, calculated risk versus reward, evasion patterns versus burst patterns, all became irrelevant the moment American shells started listening for reflections of their own radio transmissions. The fundamental shift wasn't just technological, it was epistemological. What had been predictable became unpredictable. What had been survivable through skill became unsurvivable through any means. The proximity fuse didn't just change anti-aircraft effectiveness, it changed what anti-aircraft fire meant, transformed it from area suppression to precision kill mechanism, from psychological weapon to mechanized executioner. For Japanese naval, aviation, already struggling against American numerical and industrial superiority, proximity fuses accelerated the inevitable, turned defeats into disasters, made unsustainable losses catastrophic. The elite carrier pilots who attacked Pearl Harbor, veterans who knew their aircraft and their tactics, were gone by mid-1944, replaced by hastily trained replacements facing defenses their predecessors never imagined. Technology that turned experience advantage into meaningless statistic. Vice Admiral Matome Ugaki, commanding 5th Air Fleet from a cave bunker in Kyushu, spent months organizing kamikaze units, believing spiritual superiority of pilots willing to die for their emperor would overcome American technological advantages. He never imagined those advantages included shells that could destroy aircraft without hitting them. In one of his final diary entries, hours before flying his own kamikaze mission on August 15, 1945, after Japan's surrender was announced, he wrote about incomprehensible accuracy of American anti-aircraft fire, shells that seemed guided by supernatural forces, technology that made sacrifice of thousands of young pilots meaningless in face of mechanical precision. He never knew he was describing proximity fuses, devices that helped destroy Japanese naval aviation, he commanded, contributing to casualty rates that made continued resistance impossible even for military culture that valued death over surrender. The German assessment came through post-war interrogations and captured documents. Wehrmacht commanders understood something revolutionary had happened to Allied artillery, but couldn't explain what. Attributed devastating effectiveness to superior numbers or observation, rather than accepting. Allies achieved technological breakthrough. German science had declared impossible. Dr. Friedrich Halder, who led German proximity fuse research, spent months after the war studying captured American fuses. Wrote in his technical analysis, "The Americans achieved through industrial organization what we believed required fundamental breakthroughs in physics. They solved engineering problems through mass production techniques our craftsman-based industry could never replicate." The final irony was that the secret was so well kept that most Axis combatants never understood what killed them. Died in confusion as shells exploded with impossible accuracy. Victims of technology that seemed to belong to science fiction rather than reality. Even after the war, when full story was revealed, many former Axis military officers struggled to accept such devices had existed. That defeats had been partially caused by miniaturized radios in artillery shells, technology that transformed near misses into kills and made traditional military tactics obsolete overnight. The cruiser USS Helena, where Lieutenant Red Cochran served as gun director, January 5, 1943, achieved the first combat kill with proximity fuses. That Japanese Naval dive bomber, detonating in midair 30 feet from a shell that exploded on its flank, represented not just one aircraft destroyed but the beginning of systematic technological advantage that would help win the Pacific War. Cochrane watched through binoculars as the bomber disintegrated, knew something fundamental had shifted. What had been art, men predicting heavens with gears and hope, became science. The shell no longer waited for humans' perfect guess. It listened, it sensed, it chose. In skies above battle, mathematics had changed. The consequences were difference between life and death, between invasion stalled and fleet that could move west. Victory is never product of single thing. But sometimes, single idea, turned into stubborn engineering and backed by industry and secrecy, can change balance enough to save tens of thousands of lives. The proximity fuse did not end the war, but it made fighting less fatal for those who wielded it and more decisive for those who could not counter it. That little tube of radio and metal rewrote an equation of survival and war, changed what was possible in combat, demonstrated that technological surprise, properly executed, properly produced, properly deployed, could alter strategic balance as surely as divisions or fleets. Lieutenant Hiroshi Nakamura died believing shells must hit you to kill you. That belief, held by every pilot who flew before 1943, was reasonable, was logical, was based on centuries of artillery development and decades of anti-aircraft experience. It was also wrong. And in warfare, being wrong about fundamental assumptions doesn't just cost battles, it costs lives, campaigns, wars. The echo of that engineering still shapes weapons we build. Every guided missile, every smart munition, every autonomous system that senses and decides and acts traces ancestry to those desperate wartime laboratories where physicists and engineers made impossible electronics possible, made them rugged enough to survive violence of launch, made them cheap enough to be expendable, made them numerous enough to change war. That is the legacy. Not just technology, but transformation. The understanding that munitions could think, in their limited mechanical way, could adjust, could optimize, could turn near-miss into kill through sensing rather than luck. The proximity fuse proved a principle that warfare has followed ever since. Precision multiplies effectiveness beyond simple numbers. That shells which know where targets are will always defeat shells that must guess. In the end, the Japanese never knew, never understood why their pilots died in such numbers, never grasped that American shells didn't need to hit them, just needed to get close. And in that small difference, measured in feet of empty air, lay the distance between calculated risk and mechanized slaughter. Between warfare as it had been for centuries and warfare as it would become. Between the old mathematics of survival and the new mathematics of precision kill. The sky above Pacific battles, once a realm where pilot skill and courage mattered most, became a killing field, where electronics and industry determined outcomes, where shells listened for reflections of their own transmissions and chose the perfect moment to detonate, where Japanese pilots, trained for years, veterans of dozens of missions, died confused and helpless against technology they couldn't see, couldn't understand, couldn't counter. That was the true revolution. Not just that proximity fuses worked, but that they worked so well, so reliably, so completely, that they rendered obsolete every tactical doctrine developed since aircraft first flew over battlefields, made irrelevant the hard-won knowledge of how to survive anti-aircraft fire, transformed air combat from contest of skill into demonstration of industrial and technological superiority. And it all began with a simple question: what if the shell could sense the aircraft? What if it didn't need to hit, only to approach? What if near miss could become as deadly as direct impact? The answers to those questions, worked out in laboratories and factories across industrial America, forged in the violence of test firings, and refined through millions of production units, changed naval warfare forever. The proximity fuse, 5 pounds of electronics, 130 miniaturized parts, $18 to manufacture by war's end, and worth, in terms of ships saved and sailors who came home, more than its weight in gold, more than could ever be calculated in simple exchange rates of money for metal. Because in the end, it saved lives. Allied lives, certainly, but also shortened the war, reduced the total casualties on all sides, brought conflicts to conclusion faster than they would have ended otherwise, not through mercy, but through effectiveness, through the brutal mathematics of technology that kills so efficiently that resistance becomes pointless. That is warfare's central irony, played out in the skies above the Pacific, with proximity fuses as the instrument. The more deadly your weapons, the faster wars end. The more certain your kill mechanisms, the fewer battles need to be fought. Technology that seems cruel, shells that hunt aircraft with radio precision, ultimately proves more humane than prolonged conflict with less effective weapons. Lieutenant Hiroshi Nakamura didn't die humanely. He died confused, in burning wreckage, falling into the Pacific. But his death, and thousands like it, contributed to Japan's realization that continued resistance was futile, that American technology had advanced beyond their ability to counter, that the war was lost not just in ships and aircraft and territory, but in the fundamental capacity to develop and produce weapons that could compete. The proximity fuse delivered that message with mechanical precision. Every burst, every kill, every impossible detonation that violated Japanese understanding of what artillery could do. The message was clear. You cannot win this war. We have changed the rules. We have made your skills irrelevant, your tactics obsolete, your courage meaningless against our technology. It was a message delivered not in words but in explosions, in shells that listened for echoes and chose when to detonate, in aircraft falling from sky, torn apart by shrapnel from near misses that should have been harmless, in the mathematics of attrition that turned inexorably against those who couldn't match American industrial and technological capacity. And so the war ended, not just because of proximity fuses, but because of what proximity fuses represented. The mobilization of science and industry on a scale no other nation could match. The willingness to invest billions in technology that might not work. The organizational capacity to coordinate hundreds of companies building millions of identical complex devices. The ruthless focus on making theory into reality, then reality into mass production. That was America's weapon. Not the proximity fuse itself, but the system that created it. And against that system, courage and skill and determination, though admirable, were insufficient. Technology won, industry won, organization won, and warriors who believed in spirit over matter learned, in the most final way possible, that when technology gap becomes wide enough, spirit alone cannot bridge it. The proximity fuse taught that lesson, in the Pacific, in Europe, wherever it was deployed. The lesson that near miss, properly instrumented, beats direct hit through lucky chance, that shells which sense will always defeat shells which guess, that warfare had entered new age where electronics and precision would matter more than raw firepower or numerical superiority. It was a lesson written in the sky with explosions, taught to Japanese and German warriors who died never understanding what killed them. A lesson that echoes still in every smart weapon, every guided missile, every autonomous system that senses and decides and acts. The proximity fuse showed the way, showed that munitions could be more than dumb projectiles, could be instruments of precision, could change warfare from art to science, and in that change, in that transformation from prediction to detection, from calculation to sensing, lay the future of combat. A future where technology increasingly determines outcomes, where industrial capacity matters more than individual courage, where wars are won in factories and laboratories before they are ever fought on battlefields. That is the legacy. That is what the proximity fuse meant, not just shells that exploded near aircraft instead of needing to hit them, but the principle that precision, achieved through technology and produced through industry, would define modern warfare, would separate victors from defeated, would make traditional military virtues, necessary but insufficient against adversaries who could field superior technology in overwhelming numbers. Lieutenant Hiroshi Nakamura died in 1944, killed by a shell that didn't hit him. His death was not unique, was not even particularly notable in the vast casualty lists of World War II. But his death represented something profound, the end of one era of warfare and the beginning of another, the transition from human calculation to electronic sensing, from art to science, from guesswork to precision. That transition continues. Every year, weapons become smarter, more precise, more capable of making decisions without human intervention. The proximity fuse was just the beginning, the first step in a journey toward autonomous weapons that sense and track and kill with no human in the loop. We live with the consequences of that engineering triumph, live in a world where precision strike is expected, where smart weapons are standard, where the idea that munitions should sense their targets is so commonplace we forget how revolutionary it once was, how impossible it seemed, how much genius and industry and stubborn determination it took to make shells that listened for echoes and chose when to explode. The proximity fuse changed war, changed what was possible, changed expectations and tactics, and the balance between offense and defense, changed the mathematics of survival for pilots who flew through anti-aircraft fire, changed those mathematics so completely that old assumptions became death sentences and new realities rewrote doctrine. And it all started with a simple realization: shells don't need to hit you to kill you, they just need to know where you are. The rest is electronics and industry, and the brutal logic of warfare, where effectiveness determines outcomes and technology shapes destiny. That is the story. That is what the proximity fuse meant. That is why Japanese pilots died confused, why German soldiers surrendered in despair, why Allied forces gained advantage that helped win the war. Not through magic, not through luck, but through technology that worked, produced in quantity, deployed with ruthless efficiency. The echo of that achievement still shapes our world, still influences how wars are fought and weapons are built, still reminds us that technology, properly applied, can change everything, can make impossible possible, can turn near miss into kill and transform warfare in ways that seem obvious only in retrospect. The proximity fuse, A small device with enormous consequences. Electronics that survived violence no electronics should survive. Radio waves measuring distance with deadly precision. Shells that sensed and decided and detonated at exactly the right moment to kill aircraft that thought they were safe. That was the revolution. That was the transformation. That was the answer to a question that changed naval warfare. What if shells could sense their targets? The answer? They can. They do. And once they do, everything changes. The mathematics changes. The tactics change. The possibilities change. And pilots who believed shells must hit them to kill them learn, in their final confused moments, that belief is wrong, that the rules have changed, that near miss is now as deadly as direct impact, and in that change, measured in radio frequencies and Doppler shifts and detonation timing, lies the difference between old warfare and new, between prediction and detection, between chance and precision, between survival and death in the skies above battle. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.